You know, when you see a robotic arm perfectly assemble a car, or a rover creeping across a Martian crater, it isn't just moving, it's actually calculating. Welcome to today's explainer on the calculus of kinematic autonomy. We're going to break down the absolutely wild math that bridges the gap between digital brains and physical muscle, looking at the core challenge of robotic movement and optimal trajectories.
Because it all really boils down to this one fundamental question. How exactly does a robot calculate the perfect path from point A to point B using the absolute least amount of battery possible? I mean, it sounds like a simple physical quest, right? But solving for efficiency in a messy 3D physical space is literally a giant mathematical puzzle. We aren't just telling a machine where to go, we're essentially forcing it to balance its energy output with the unforgiving laws of physics. So, here is how we're going to unpack this today. 1. Finding the perfect path. 2. The math of movement. 3. Physics in real time. 4. Hardware limits and pitfalls. And finally, 5. Perfection versus functional safety. Okay, let's dive into this.
Section 1. Finding the perfect path, optimal trajectories. To pull off kinematic autonomy, these machines have to meticulously plan literally every millimeter of their movement to hit a goal while keeping costs like time or power to an absolute minimum. Which brings us to Section 2, the math of movement, nonlinear programming. Now, to get this, we absolutely have to talk about the optimization cost function. It's basically the mathematical formula used to balance a robot's ultimate objective against its given physical constraints. Think about it like this. Imagine the objective is just grabbing a cup of coffee. Your constraints? Well, the length of the robot's arm, the weight of the cup, and maybe the table sitting right in the way. The cost function weighs the whole shebang to find the single best sequence of joint movements that grabs the cup without, smashing the table or blowing out a motor.
Inside that mathematical brain, the robot is mostly dealing with two types of optimization, convex and non-convex. Convex optimization is kind of like finding the bottom of a smooth, perfectly round bowl. There's one clear, mathematically predictable answer. But non-convex optimization, way harder. It's like dropping a marble into an egg carton. There are all these little dips and valleys, meaning multiple potential paths, but only one is the absolute deepest or best. And honestly, this is exactly what a robot faces when it maps a cluttered room. The math gets super bumpy, and finding that perfect path becomes non-convex. So how does this abstract math turn into physical action?
Well, the machine tackles this bumpy math using a pretty precise recipe. Step 1, define the objective, like moving from point X to point Y. Step 2, map the constraints. So the robot defines an obstacle constraint in its 2D grid, marking exactly where a desk or a wall is so it knows what space is mathematically forbidden. Then, step 3, optimize the torques. It calculates exactly how much electrical current to send to each specific joint motor to smoothly navigate around that forbidden zone. It's just a continuous, rapid-fire calculation of limits and goals.
Moving on to Section 3, physics in real time, calculating dynamics. So, when a robot is tasked with some serious heavy lifting, it relies on something called Newton-Euler recursive dynamics. This is exactly how the robot handles constraints in what engineers call task space. Simply put, it's a way for the robot to quickly calculate the forces and torques acting on every single link of its arm, starting all the way from the base, out to the gripper, and back again. By using these Newton-Euler equations, the robot optimizes its joint torques on the fly, making sure it doesn't just tip over or snap a gear when it picks up a heavy payload. It really shows how deep physics is baked straight into the software.
And we literally couldn't do this without foundational work like Roy Featherstone's spatial vector algorithms. Featherstone created a mathematical notation that totally revolutionized and simplified how we calculate rigid body dynamics. Because of this elegant math, high-fidelity physics simulators, like the super popular Gazebo software, can calculate these incredibly dense dynamics in real time. Engineers can basically simulate exactly how a multi-million-dollar robot is going to behave before they even hit the power button. It's a real game changer.
Now, to actually pull these movements off in the real world, modern autonomy heavily relies on model predictive control, or MPC. If you look at MPC versus traditional PID control, the difference is wild. PID control is purely reactive. It looks at where the robot is versus where it should be and just nudges it toward the goal. But MPC is predictive. It uses an internal math model to simulate the future, optimizing a trajectory several steps ahead while constantly factoring in current physical constraints. It's essentially playing a high-stakes game of chess with its own moving parts.
And because of this massive predictive power, these dynamic mathematical technologies are the backbone of some incredibly demanding fields. I mean, think about high-speed manufacturing. You've got robotic arms whipping around assembly lines with millimeter precision, dodging collisions at blinding speeds. Or space exploration, where a rover millions of miles from Earth has to autonomously calculate the most optimal, energy-saving trajectories over completely unpredictable alien terrain.
All right, Section 4, Hardware Limits and Implementation Pitfalls.
Because it's not all perfect math. One of the biggest hurdles engineers face is figuring out if it's even feasible to run heavy calculations like that model predictive control on low-power microcontrollers. A robot operating out in the field is usually on a super strict energy budget. If the math demands way too much processing power, the robot's brain might actually drain its battery faster than its motors do. And beyond the hardware limits, we run into some pretty deep algorithmic traps.
The absolute most notorious of these traps, that's what we call a local minima. This is what happens when a multi-million-dollar, highly advanced robot gets completely stuck in a mathematical valley. Remember our egg carton analogy from earlier? The robot finds a little dip that seems like the absolute best spot nearby, and the math insists that moving in literally any other direction is mathematically worse, so it just stops. It is the robotic equivalent of a human confidently walking into a room and then totally forgetting why they went in there in the first place.
Now, what's really interesting about this slide is how we can actually visualize a robot trying to think its way out of these traps using an optimizer convergence plot. It shows the algorithm churning through hundreds of calculations over time. The graph starts high, which means high cost or inefficiency, and then you watch it sharply drop and eventually level off. When it levels off nice and smooth, the optimizer has converged. It found its path, but if it levels off way too early, well, it's probably stuck in one of those local minima we just talked about.
Which brings us to our final section, Section 5, Perfection versus Functional Safety, the Ultimate Debate.
If you look at the foundational textbook, Convex Optimization by Boyd and Vandenberghe, you'll see the pure, undeniable beauty of mathematical perfection. When the equations are perfectly convex, the solution is just flawless. But the real world, it is definitely not flawlessly convex. It's messy, it's full of unpredictable friction, sudden obstacles, and degrading hardware. Sometimes, the path that is mathematically perfect on paper forces the robot to operate so close to its absolute physical limits that a tiny gust of wind, or maybe a slightly heavier payload, could cause a total catastrophic failure.
So, I want to leave you with this final, lingering question to think about. Should autonomous robots always strive to be mathematically perfect, squeezing out every last drop of theoretical efficiency? Or, in our messy, unpredictable real world, is a trajectory that is mathematically just good enough, actually safer and far more reliable? Thank you so much for exploring the complex calculus of kinematic autonomy with me today. Keep questioning the algorithms around you, and I'll catch you in the next explainer.